Alrighty, so let's try this again. This time with some audio working. Looks like the headset got muted about 11 minutes into the previous video. So we're going to re-record the relevant pieces starting from about where the audio cuts out, where I was going to explain particularly the parts of this diagram you do and do not need to be modeling. Okay, so because we are dealing with straight line code, you do not need any predictive structures. Because we are not modeling the specific addresses of memory, you do not need the ITLB and iCache. Likewise, you do not need the dcache or DTLB modeling. Because we are dealing with the ordering among operations and not the actual values of what they're computing, which should be reasonably obvious from the format that you were given. Like, it doesn't say what type of register instruction, just that there was a register instruction. We don't actually need the contents of the register file. We're just tracking IDs. We don't need an architecture register file either. We don't need the actual values of anything to do this work. You are going to need to have a map table. Fortunately, this is literally just an array. I will come back to that in a second. You will need a free list. This will be a FIFO. You'll need a ready table. This is also an array. So let me just sort of indicate this here. All right, this is just an array. This is just an array. Right, and this is a some sort of FIFO. Okay. And the sizing on the map table is going to be known. This is exactly going to be 32 entries. Right, so you have index 0 down to index 31, indexed by the architectural register number. Right, and it just tells you the this dimension here is the physical register number. So an array of 32, ints, 32 integers. Yep, pretty straightforward. Okay, now the ready table, you don't know how big it is until you read the file, because the ready table is sized as a function of the number of physical registers. All right, so this is going to be 0, i.e. physical register 0, an index of 0 up to whatever the number of physical registers, minus 1. Right, so preg, number thereof, 0 up to minus 1. Okay, and this ready table is just 1 bit wide. Right, so this is true or false. You don't have to actually make it 1 bit. You could, store a word, store a bool, whatever your language's favorite flavor is. Okay, we are collapsing all of this into issue. So don't worry too much about how fast this out of order processor would actually run in terms of clock cycle. It would be pretty slow. We're doing a lot of work here. This is all from the perspective of our scheduler. This is all just the issue stage. Okay, now what's going on in the rest of this? We don't need all of the properties of the ROB, but we do need to keep track of things, and we do need to keep order. We only need the ordering property here for the LSQ, so this is only a little bit implemented, right? So we're not going to looking at the forwarding, because again, we're not looking at the actual values of anything. We're doing conservative scheduling, so we just need to do ordering. We'll talk a little bit more about load and store ordering in conservative scheduling in just a second. Okay. You are going to basically be modeling fetch, decode, rename, dispatch, issue, write back, commit, some flavor of issue queue, right, which is going to be some sort of associative search structure, right? So that could be a map-based index structure. Could just literally walk through every possible entry. We're not going to judge you on the efficiency of implementing this. This of course does have FIFO properties on the ROB. IQ does not. Okay, so when we're looking at modeling all of these, what do we mean by modeling a fetch stage, right? We're not worried about the particular mechanics of exactly touching memory, since we're not. So really, you want to abstract it as there being a set of instructions, so some stream of instructions. And what is the role of fetch? right? Well, fetch is going to take, if we are n wide, right? So n wide, just sort of leave this here. All right, so then we're going to take n instructions. Oops, so fetch's job is from all remaining inst. We are going to produce the next n instructions and send them to decode. So logically, you can sort of think of this as actually there being sort of a queue. It's definitely FIFO of instructions, right? That feeds into the fetch stage, and then decode, right, has a queue of instructions that are yet to be decoded, right? And then that is just going to send them across to rename, right? And so on and so forth. So we basically just have a series of queues that are just moving data across. Right, so these instructions haven't been fetched yet. After fetch, they've been fetched but not decoded, right? And then after decode stage, they've been decoded but not renamed, right? And after rename, we're going to put them in a set of instructions that have been renamed but not dispatched, right? It's DE, just for disambiguation. And then dispatch, we're going to send them into, now this is a little bit different, right? Now we're going to send them into, rather than some FIFO queue, we're going to send them into the issue queue, right? Which is a structure that they could be leaving in any order from, right? So rather, each of these is sort of n wide in order, n wide in order, right? Here, we might stall, right? So it might be less than n. It's the first place in our system we could stall if we run out of renaming registers, right? So this is less than or equal to n, right? Dispatch won't stall. So if it's got, so the only thing that, well, it could have less than n work to do if there's nothing in this queue, right? But and then the IQ again is going out in no particular order, is going out in the order that things are ready, not in the order that they were put in. Okay. And then these are then going to head into again write back. You have a queue of things which have really so at least logically speaking, right? These are going to be a bunch of singletons, go into this write back queue, right? So things that haven't been written back yet. Write back will write them back. Again, we're not actually updating the values, so not a whole lot for write back to do, other than mark things as done, right? And then the other queue that we have here, let's see, there is dispatch. So we're also sort of going to put this in the ROB, right? And so this is what, so write back's really going to actually modify locations in the ROB, at least logically, right? And then the ROB is what's actually then feeding commit, right? Where it actually commits up to n instructions. Okay, so really most of this is just, I have a set of inputs. The inputs are things that haven't done my stage yet. I'm going to put up to n of them into the next stage, unless there's some reason that I can't do the work, right? Unless I've run out of a resource that is required. Since we don't say that these sizes here are ever going to be small enough to stall here, we will stall in rename if we run out of physical registers, and we will not issue if instructions are not ready. Everything else is can do up to n wide. Okay. So in terms of initialization, right? My map table where we're given that architectural 0 is in physical 0 up through architectural 31 is in physical 31. The contents of the ready table, those registers that are thusly mapped since the pipeline is initially empty, right? The first 32 entries are all ready, right? They have valid data in them, and 32 onwards are have no valid data in them. And similarly, the free list is basically going to be 32 up to preg number -1. So minus. Right. So this free list is just going to contain everything, all the additional register identifiers, physical register identifiers, starting from 32 up to whatever the number you're given is. Okay. So in the initial state, these are all available, and they're all, well, contain no actual useful data. Right? They're free, so they're not ready. Nothing has produced the value that is in them yet. Right? So you'll fetch some instructions. What's going to happen? Go wrong. You'll decode some instructions. Now, you could have pre-decoded them. We have no control flow in this, so you'd have to sort of figure out which instructions happen when. We're not modifying the state of the machine based on when you decode them, because it's not that type of ISA. So you could actually have technically pre-decoded everything. You don't actually have to have fetch sling text, right? You could actually already have populated the relevant data structures and just sort of pretend that you don't decode it until decode. It would be the same either way. Simple scalar cheats in a somewhat similar fashion, although it has actual addresses. So it's a little more reasonable for it to actually move things in a little more modeling in fetch. Here we don't have that modeling, right? So we can just assume perfect alignment and all that. But whether you decoded them as soon as you read them from the text file, or you decide to wait and actually do decode during decode, all this is going to do is set up what the source registers are, what the destination registers are, just make sure that all of the structures that you're going to read further down the line have been properly initialized with the particular values of that instruction, right? So if I have a register instruction, I have one destination and two source registers. I know the architectural versions of these by the end of decode. If not, again, during initialization, you should have mapped that into a record of that instruction, that what its architectural register needs were. Then you go into rename. Rename is going to pull from the queue of decoded instructions, say, okay, do you define anything? Because remember, stores don't define anything, so you might not actually need a entry from the free list. If you don't define anything, great. That'll be very simple. Whether or not you find anything, you definitely have operands that you need. So we'll check for these based on the type of instruction, right? So some of them, like immediate, I don't need to go get the immediate from a physical register. It's just there already. But I'll check out all of the architectural registers that I'm naming. I will look up what their current mapping is in the map table, right? I will enter in what the current value from that, so if I look up register 2, register 2, I'm going to go here, and whatever this current value is, I'm going to record that in my structure and say this is my renamed mapping of this particular instruction. It reads from this logical register, right? And then if it defines anything, I'll pull something from the free list and say that's the register it defines. Then during dispatch, right, you will make sure that the readiness based on the ready table of these is set properly. So anything that you are defining, you have to make sure that it is in fact set to false. Right? If I'm defining register 16, I need to make sure that it is, after dispatch, set to false. It's not ready yet. It hasn't been computed until this instruction actually issues. Right? And that's about all there is there. Right? Again, technically, we would throw it into the ROB and the IQ. So it is going to actually push it into some IQ structure you can associate with search. It will need to be in something that acts like an ROB and remembers all of your progress all the way through here. For this assignment, it's not that ridiculous to actually sort of just have a global structure, since we know that there's a finite number of instructions that we're going to ask you to execute at max. So you could just have some sort of pre-allocated array of these rather than explicitly worry about pushing them in and out of the ROB. Up to you how much fidelity you want. We're really just worried about getting the timing right. Okay, and the timing doesn't care about that implementation detail. Okay, so once it's in the issue queue, you are going to basically want to do select and wake up. So there's going to be some set of things in the issue queue with priority by age. Right, the longer they've been there, the more we want to send them out. And if their inputs are ready, then and you have not yet sent instructions to issue in that cycle, then you should issue it. Right? If their inputs are not ready, then you'll wait. Now, whatever that you have actually sent, right, you can then mark whatever it was defining as being ready, so that in the next cycle, right, you will allow it to update. Now, just a little quick something. If you alternate between issuing and then setting the flags and then trying to issue again and setting the flags and issuing and setting the flags, you'll issue dependent instructions in the same cycle, right? So if I have, this is what you do not want to do because that does not make any sense. Let's say that I had originally some R2, 2, R2, 2, 2, right? So after these get renamed, this would be something like, let's say this is your entire program. This would be R type 32, 2, physical 2, and then R physical 33, physical 32, physical 32. So either you want to actually sort of collect all the things that have been made available, right, and not mark them until you have attempted to schedule all of the things that are in your issue queue. So i.e. at the logical end of the cycle. So you can just remember these and do them at the end of the cycle. Or talking about in a second, you could be a little sloppy. You could have them actually be woken up by write back. In general, this won't work, but in our exactly depth to pipeline, it's equivalent. Right, so you get a write back to the wake up instead. You avoid accidentally issuing this and this in the same cycle by trying to update ready table right after you do this and then delaying it. The other model is that you could actually, in all of your modeling, really sort of have a logical clocked behavior, right, where you actually have the sort of live version that only gets updated here, and then you have I guess that's a negative edge clock. Let's do a positive edge. Here we go. I have a live version that's only going to get updated. Right, so here, right, and here, and then what you would have is a sort of working version. Right, you have another variable, another structure, or you could wrap around a structure. So you basically have internally, right, here are the things that are being updated during the cycle. It'll remember them for you, and here's the actual state of the structure that's readable. So you only read from this, and you only write into this, and then this transition here is handled only sort of on the logical clock by some function. Right, that's a perfectly reasonable way to do it. And if you wanted to do sort of a general modeling of synchronous hardware, something like this is actually what you want to probably do. Given that this is an almost entirely feed forward, right? So our only backwards loop in this is from commit to the free list, which is used in rename. So you do need to make sure you don't blow through and make this available in the free list cycle early. The schedules will help you validate that. But other than that, everything is feed forward. So since everything is feed forward, we can just do the same trick that the Simple Scaler did and just run the pipeline backwards. And then if I read this before I write into it, right, then I don't need this sort of separate structure and this explicit clocking function. So it's a little simpler on the coding side, a little less robust if you want to do more complicated things later. Right? But good enough for this assignment. Okay, so let me pop over to a whiteboard. Let me also just sanity check. Am I still? Yeah, audio didn't cut out this time. Good on us. Pop over to whiteboard, and I just want to go over conservative load store ordering. So let's say we have a store, still load, a store, a couple of loads, a store, a couple of loads, and a store. And we want to look at what are the dependencies again, because again, we don't rename memory the way we rename registers, right? So each of these is right here is we're sort of defining sort of logical new updated versions of memory. And so the issue is, since we don't know what the address is, we have potential dependencies. Like we don't know if they're dependent or not, but they might be. So there might be a read after write, right? This store might define the value that these loads are supposed to load. We don't know until we compute the addresses. And in this model where everything happens in issue, and we haven't split up our load and store address calculations, it effectively means that these loads are going to be scheduled as if they're dependent on the output of the store. Even though it's not the output of the store, they're dependent on the address calculation that was part of the set of things that happened when we issued this store, right? Okay. So this, again, we don't know if it's going to the same place. Oops, let me draw the arrow. Right. This doesn't have a race. Okay. Draw the arrow going that way. So this is a right after right, potentially. Again, these are all unknown, right? So in conservative ordering, what we're going to do is assume that every arc that might exist does exist, right? So this might be a right after right. This might be a right after read, right? This might be a right after read. We don't know. Right? And again, renaming didn't fix this for us because we don't rename our loads and stores. And the same pattern is going to go out here, right? So this load doesn't have to worry about the total sequential set of all possible stores in conservative ordering, because we're never skipping them. We're treating them always as if they're dependent. And so if you were looking at in a aggressive version, we would really actually have to check all older stores. But here, because we've already serialized all the stores and all the loads relative to the stores, it's actually sufficient transitively to just check the closest one. Right? And this pattern will play out the same way. So I can't get a lot of parallelism here, right? So I can schedule these two in any order, with respect to each other, but I can't move the loads after the stores. I can't move the loads before the stores, right? So this is a, sorry, pick a different color. This is a no-no, and doing this after is also a no-no. So we're really actually very, very serialized in the conservative model. Right? Conservative model assume that all these dependencies that might happen do happen, and do not schedule them until you actually know the address. Again, this wouldn't be quite as bad as we're depicting it in practice. So imagine that you've got some some pattern where your store, right? Your store needs a value and it needs an address, right? And then if it has both of these, right, then it can send to store buffer. It may often be the case that the address, like let's say that basically I'm just going to say, foo, right, equals f of bar. Let's do all caps. I feel like all caps. Okay, so this may take quite a while to compute, right, and to arrive at the value, right? But where foo is may be very easy. In this case, it'll probably be just somewhere on a stack, right? The address of foo may be known, in like one instruction, right? Just some offset from the stack pointer, right? So this may be a one instruction dependence chain. This might be some complex dependence graph of its own, right? So you do often actually get the case where I can figure out whether this foo, let's say I've got some other thing later, right? ... in my code, and then I got some, I don't know, qx equals a of I. Right, now basically want to figure out, is this location the same as this location? Right. That we may be able to figure out very, very quickly. So we're not necessarily actually dependent on the store happening, we're dependent on just the address portion of this. But again, in our example, we've simplified it to the point where we can't really differentiate that. Needless to say, conservative ordering is slower, and you do actually want to speculate in general, but exactly implementing that is a bit beyond. Well, implementing is beyond the scope of this class. Scheduling it, we've already seen on the last week's out of order problems, right? And that's all the stuff we've been doing in class has been using aggressive scheduling, but conservative scheduling is very simple. Okay, so that should cover just about all the stuff you really needed the audio for. I'm not going to re-record looking at reading from a comma-separated value file. Hopefully, that's both simple and the code I showed is reasonably self-evident. But I did want to get these two things re-recorded so that we can get everyone up to speed. If you didn't catch this on Friday's recitation. Okay, take care, and hopefully third time's the charm. And this actually is a decent quality audio version of the major important points.